Hello, everyone, and welcome to Geospatial Analysis with Python. I'm John Hogue. I'm a senior data scientist at General Mills and co-founder of Social Data Science, a nonprofit that connects aspiring as well as practicing data scientists together to work on data sets throughout the community using real data, real problems, using real code. And one of the reasons why I put this talk together is because we put on a competition back in November, which was called MinneMUDAC, and we looked at the association that water quality had with property values. And a lot of that data was in geospatial files. And the students that we were working with had never really worked with this information. And so we didn't want to just provide them a data format that they've never worked with and discourage a lot of people from participating. So we took it on ourselves to kind of pre-prepare this data. And I just wanted to share kind of the key learnings that I had based on preparing that data. So disclaimer is that, I'm not a GIS expert, so if I misspeak or if I say something that's wrong, leave a comment, let me know, so I can make sure that I don't repeat that mistake in the future. I just learned this kind of on my own. All this information's out on the web, easy to learn. And the key thing is that, I'm going to be mostly talking about shapefiles. There's other formats out there: GeoJSON, Raster, key markup language, or I think it's keyhole markup language. And then lastly, I'm going to be working with Python 3.6. I know that this works on Python 3.4 and 3.5. I'm not going to guarantee that this works on 2.7. Honestly, my organizations have all moved to 3, so I don't look back at 2 anymore. So I'll go through a background of what is geospatial data, the types of data that's available, and where you can possibly get some of this, specifically related to Minnesota geospatial data. Then we'll get right into the technical part where put your seatbelts on and we'll go into a deep dive on this stuff. So we'll set up an environment, we'll read in some data, we'll explore some data, do some filtering, then we'll kind of get into the geodesic information. So we'll do some transformations, we'll do some calculations, we'll do some joins and merges, and then we'll create some new data to be able to use in analysis, and then we'll write the data out. Given that, let's get into it. So what is geospatial data? When you think about this, this is really how we try to represent the world around us in a format that is easily read by a computer. Computers want everything kind of in a numerical format. The world around us is very complex, so we try to model it in different ways. And so geospatial data can mean anything that is tied to anything in geography. It could be coordinates, it could be an address, it could be a zip code, it could be a city, it could be a park, it could be a lake, it could be a series of power lines. This is all geospatial information. And the way we might try to represent this information is kind of depicted in this picture. So at the bottom here, we've got kind of the real world. It's 3D, has multiple layers of information in there. You can see there's bedrock information in here. There's the water table. There's the sediment. There's trees here. There's elevation. There's waterways. There's roads. There's cities. All sorts of different information here. But it's kind of hard to represent that all in one file, and you might not care about all that information anyways. So there's multiple ways that we might layer these things on. So geospatial information often talks about layers. And so one of them might be a raster layer, which is basically a picture that's trying to figure out kind of the elevation or kind of the density of colors to try to determine kind of land usage or something like that. Then we have this other set of information. It's called vector data, and this is where you're using points, lines, and polygons to definitively define specific points of interest, specific roads, boundaries for cities or states or something like that. using mathematical polygons on this. So it's very well defined, whereas the raster data is very fuzzy. So as I mentioned, there's two different kinds. We're going to mostly be working with the vector polygon data. This is what's shown up in the shapefiles. There's a couple other formats out there: GeoJSON, keyhole markup language, which I think is what Google uses. But basically, this is useful for storing information about geospatial things that are discrete. So county or country borders, what land is around your house, commercial zoning, things like that are very clearly defined. It also can include line objects like power lines, roads, sewer lines, things like that. And I would say that this is most often going to be what I'm going to be using as a data scientist to enrich other data sets that I have. So in our example, we wanted to compare the parcels near a lake to say how close are they to a lake, and if we tie in water quality, as that water quality changes, how does that change the valuation of that property? So we had to kind of create that based on this vector polygon information. Another thing to keep in mind is that by using this vector data, is you can appropriately weight your attributes based on the area or density. So if you can think of downtown Manhattan, the population density is much, much higher than somewhere out in the middle of Wyoming. And so you don't want to just compare apples to oranges. You might want to create a richer set of information to model your stuff off of. The second set of information that I alluded to was raster data. And this is literally just image data. It could be satellite, it could be aerial photography. As drones become more popular, they're using drones to kind of take additional micro samples of farms and things like that. They're hooking up things like LiDAR to take topography readings to tell tractors exactly where to put specific fertilizers and plant certain seeds to maximize crop yields. This information is usually pretty fuzzy, and so it's more of a image recognition type problem. So an image like this, you might run like a neural net on it to try to determine how much of the land is being used for farming, how much of it is being used for cities or something like that. You might also be able to determine the state of drought that the county is in based on historical data. How green should this land be versus how brown it is now? So we're not going to really talk about this information, but that information is out there. And then, the last bit of information is probably what you guys are most likely to use in your day jobs. This is tabular information. This is kind of what we provided to the students eventually. And this is just numeric data that's just tied to a geographic component or a key. So this one here, this really bad JPEG file of a flat file, shows a geography identifier. This could easily be a zip code, it could be a state, it could be a city name, you name it, and then you've got all the attributes that go out to the side on that. So this is typically what most data scientists and statisticians are going to work with, but keep in mind that, like I said, if they aren't appropriately weighting this information based on the density, maybe that's not a good measure for you. We were working on some information where we want to look at like a competitive index. Well, certain counties are 10 times bigger than other counties, so if there's 10 gas stations in that area, that's going to be a lot less competitive than an area that is much, much smaller but has 3 gas stations. So kind of keeping that in mind, you might want to kind of roll your own attributes by going back to kind of the source information. So I mentioned kind of in passing what kind of geospatial data is available, but typically it falls into these 5 different groups. There's biology information, so what kind of animals or plants are in certain areas, what's their population. You might track the expansion of invasive species over land usage or water. You might use it for boundaries to identify where a school district ends or where the city line ends. You might use it for the environment as what we're going to use here. So we might track the water quality or the runoff from certain lakes to see how that changes over time, or just kind of plot it out through different events. Climatology, you might include topography as well as kind of other information around like how many lakes there are in the area, because that's going to affect the amount of moisture there's going to be in the air. And then lastly is economy, which is what most people I think of when they think of this information. This is kind of where are the areas that are suffering most from poverty. Where is the most dense population areas, etc. And multiple areas create this information, but most of it I find is created by the government. So this could be local. So in the Minneapolis and St. Paul area, we've got Met Council. We've got the Minneapolis School District. You've got various local agencies creating geospatial information to be used by the local government. Statewide, you've got the DNR, Department of Natural Resources, the Pollution Control Agency. You've got the county level kind of information there. And then federal, you've got things like Census Bureau, NASA, Bureau of Labor Statistics, etc. But just because government provides a lot of this information doesn't mean that private industry isn't creating this data or using it itself. Energy is going to be a main proponent of this. I've got many friends that are working for energy companies, whether it is actually getting oil and gas, identifying kind of where there are deposits of minerals or other precious elements under the ground. It may be these power companies that want to identify where do we have our power plants and where are our substations and how does it get distributed across different population centers. And then last but not least, technology companies. Google and Uber are going to definitely use this to make sure you can get from point A to point B faster. Google's always using things like now on my phone, it's telling me, are you near Walgreens? Here are some ads for Walgreens if you go into Walgreens. So they're definitely using geospatial information there, and I hope that you guys start considering using that after this. Where are some great areas to get some geospatial information? There's Minnesota Geospatial Commons. There's many other information or websites like this out there. This one I really appreciate because it was put together by the community for the community. So we've got an organization in town called Open Twin Cities that kind of partnered with multiple government organizations to kind of collate the information into one spot and provide some documentation on it. So I really appreciate this. The link is within this document, which all of this document is an IPython notebook, and I will share the GitHub link at the end of this talk so that you guys can try it out on your own. So, I want to kind of dispel this myth that, to do geospatial analysis, you need to use expensive proprietary software like, I think it's called ARC. You don't actually have to use that. You can just use regular Python. There's plenty of libraries out there that mimic a lot of this. I know that a lot of those proprietary systems are now tying into Python to be able to provide additional scripting or additional enhancements that previously weren't there. So definitely recommend using Python. You've got nothing to spend money on. You can try this out, see how well it works. That said, support is all based on the community. So I'm giving back to the community by giving this talk. I hope that if you guys find out some stuff that you guys contribute back and let other people know what you guys have found out. So getting set up, I'm going to quickly cover this because this is kind of boring stuff, but you need it if you want to run this stuff. So I'll first start out with saying, like, if you're going to do data science stuff within Python, do yourself a huge favor and just get Anaconda. It's from Continuum Analytics. It's just a distribution that contains a ton of scientific computing libraries already bundled with Python. And without using Anaconda, you're going to spend like an entire afternoon, if not like a couple days, trying to get all these things installed and managing the dependencies on these things. It's a huge headache to do it by yourself. They've done the community a great service by providing this. Go out there and grab this, download it. It will solve probably about 90% of the packages that you will ever need, and it makes the other 10% super easy to install. Speaking of other languages or other packages that you might want to install, there's Conda Forge. And so this is something kind of similar to PyPy or pip, but it's more for scientific computing libraries. So it handles a lot more library dependencies that are outside of Python. So Python has a lot of things that are compiled down to C, and pip doesn't really handle those unless people are really on the ball and creating universal binaries, which most people are not. So Conda Forge allows you to kind of compile these things for your Windows computer, your Mac, your Linux, really easily, all just writing a simple command, which I'll show you later. So definitely recommend using Conda Forge for installing this stuff. So with that said, to add Conda Forge to your repository list, you can just run this cell here. It just adds it to the top of your list, and we'll start installing things from there. The libraries that I'm going to talk about, mostly I'm going to talk about Geo Pandas. Some of the things that I talk about in here are more specifically related to some of the dependencies that Geo Pandas uses, like Shapely and R-Tree. But you can kind of read about these here. I've got a more exhaustive list of other geospatial libraries that are available out there. But check them out. They're all open source. The ones I have listed here have great documentation on them. GeoPandas basically works just like Pandas if you've ever used that within Python. And then Shapely and Fiona are also just really great documentation on those. So I really enjoyed working with those, and it made learning this stuff really quick. So to install those, you can just run this cell here. This will install everything. It will not ask you, do you want to install this? That's what that yes does. If you're going to install these things from IPython, you need to have that -yes there. Otherwise, it will just kind of behind the scenes be waiting for that yes to be run, which IPython will never see. So just include that in there, but just be forewarned that it will install that stuff automatically and won't ask you about it. I've also got a couple kind of custom GitHub packages that I really like. They're not as popular, but I'd like to shine some spotlight on those. One is Panda Summary. It generates a ton of profile statistics on Pandas data frame. GeoPlotLib allows us to kind of plot some of these geospatial features that we're going to be looking at. And MissingNo allows us to look at missing data very easily and identify kind of what's going on with our information really quickly. So you can install those by directly installing the zip files from the GitHub repositories. Again, the links are included within here if you want to read more about those packages. Or if you find that, hey, there's something that you wanted to add to them, feel free to contribute. I'm sure that they would love a pull request. So that was a lot of talking about getting ready. What is geospatial information? You guys are probably ready to get your hands dirty with this geospatial information. So the data set that we're going to look at is the Metro GIS Tax Parcels 2014 data set. So what this is this is basically all of the individual properties, parks, government areas across the 7 metropolitan counties within the Twin Cities area. And so anything that's a park, my house, the local businesses, they're all going to have an individual Polygon representation of those on here, along with tax information for those. So how much is the house worth? How much is the land worth? Does it have any special assessments against it? Things like that. So with that, let's dig into this. First thing first, if you download this repository online, everything's all zipped up, and it may be alarming to realize that once you extract this zip file, it will take about a gig of free space. I've already run this, so I'm not going to make you guys wait for this to unzip, but basically it's just going to unzip this data file so that you guys don't have to wait on that to run. I've also linked the official PDFs to the metadata. So there's tax parcel metadata here. I don't want to really screw up the presentation here. Believe me that it gives a bunch of information about when the data was collected, how long ago it was collected, what the amount of information collected or what types of information are available for each county. And then there's a field description metadata file here that describes what each field represents. As data scientists, we should definitely make sure that we read through metadata because there's a lot of important information in there, and it can save us a lot of time. If you read through this metadata, you'll find out that certain counties were keeping track of what they call like multi-polygon parcels, which happen to be condos. Other counties were keeping track of the entire condominium complex as a single tax parcel. So looking at those things may change how you view this information. So highly recommend you look at metadata before you get too far into your analysis because you can make the wrong assumptions. So reading in this data, I'm just going to kick this off and start explaining it because it does take a while. It's about an 800 megabyte file. So we're going to be using this Geo Pandas library. We're going to import it in right here, and then we're going to point it to where the file is. If you were to go in and look at the files within that folder, the MetroGIS tax parcels folder, you're going to find that there's not one file, but about 5 or 6 different files. And all these files work together to kind of create a database of geospatial information. And so you really only need to point at one of them, and Geo Pandas is smart enough to figure out what to do with the rest of them. So you don't have to worry too much about it. This is a shapefile, as I mentioned, and it is about 800 megabytes. So it's going to load for a little bit. And it's going to put it into a data frame called Hennepin, which is the county where Minneapolis is located. So while that runs, I'll also just explain some of the common default settings I have for an IPython notebook. I'll run that real quick. It changed my view on the screen, but I'm going to use this %matplotlib inline. And basically what this is it's not a library, but it's a magic function that enables plotting to happen within your IPython notebook, so it doesn't pop up another window or another tab. So highly recommend always enabling that. And then I'm importing, the standard pandas, which is kind of the bread and butter for data analysis and data wrangling for Python. NumPy is kind of the numeric library that Pandas is built on, but if I want to do some additional calculations, I'll use NumPy. And then matplotlib is the bare bones plotting library that basically every other plotting library within Python is built off of. It's kind of ugly and rudimentary, but when we're doing data exploration, I don't always need things to be pretty. I just need them to be fast, and I need them to be quick and easy. So I recommend bringing that in. And then the rest of these things are more just options that I like to set on them. We live in a world where we have widescreen computers now, so I don't necessarily want to look at everything as if it was in like the 4:3 ratio. So all this one does is just makes it so that it takes full screen, so I can see everything. Likewise, I don't want IPython to just only give me a subset of columns and put like a ... in the middle. Setting this option allows me to see all the columns, so I don't have to wonder kind of what's happening in the middle. I can just scroll over. That's why they've got a scroll bar. And then I also don't like looking at scientific notation, so I just make sure that I set that so that it doesn't use that. And then lastly, because I am on a high resolution screen, I wanted to make the plot sizes a little bit bigger. So I just set those to be a little bit bigger. So Looking back, we can see that this finally did import. So if I want to get a good feeling for this data, we can run this .info. We can see that we've got 427,000 entries. So that's that many records or rows. And then you can see all the columns in here. We've got 70 columns available. You can see their data types that they're set as. Basically, anything that's object means that it's not numeric. So you can see that we actually have 55 columns that are not numeric, and that we're using 228 megabytes. So 228 megabytes might not seem like a lot when you got a computer that has 8 gigabytes or 16 gigabytes, or maybe you're on a more specialized computer that has more memory than that. But really lugging around that much data just makes things just that much slower. So we might want to take some time just to make sure that we're being more efficient about this. So you'll notice, though, that 228 megabytes is a lot smaller than the 800 megabytes that we started with. And this is because the numeric data was stored as text in the shapefile, so that when it brings it in, it's able to kind of collapse that down. So each character takes up 8 bytes, whereas numeric data usually only takes up like a couple bytes. So it ends up being a lot smaller, and you get a much more efficient format once it's in memory. But let's do a couple things to kind of make sure that we're working with this data more efficiently. First, let's set an index, but when we want to set an index, we need to make sure that everything is unique. Otherwise, you're not going to be able to find that specific index point. So one thing that we can do is, if we looked at the metadata, it said that this field called PIN was the unique identifier, but sometimes we can't trust our sources, so let's just verify that. So we're going to count the number of uniques and then divide it by the total number of records, and we hope that we get 10. Perfect, they're all unique. So now we can set the index, and we're just going to sort it. So we do that, and what this enables us to do is traverse that data much faster. But as you recall, when I said that there was a lot of data in there that happened to be spring type, or not spring type, but string type, it's not very efficient because it's going to use up a ton of extra space. A great example of this is this green acre column. It's just yes or no. We don't need to have all of the additional string methods attached to this, like length, replace, any other type of upper or lower type methods. We just need to treat this as something a lot more simple. So we can convert this to category type, and basically what this is Python behind the scenes creates kind of a hash map, which converts these to numeric, and then has a mapping to those behind the scenes to get them back to the character type. So then, rather than having 400,000 no values, each taking up 8 bytes, instead you've got maybe a 0 that takes up 1 byte. So much more efficient. But the thing is that there's probably a lot more of these columns out there than just this one. So I might kind of want to go through these and do them all in one group. So what I can do is I can create a list of all the columns that are available, and basically only include those that are this object type. So anything that's not numeric, and then I'm going to get the names of the columns, and I'm going to then just print out how many there are. So there's 54 columns that are all object type. But like I said, I don't really want to go through and go through and convert all these one at a time. So this is a great way that I think data science kind of differentiates itself from kind of traditional statistics, is we create reusable tools to solve problems for us, so that we're not kind of doing stuff one-off, but rather creating things that are more reusable and sustainable. So what I've created here is I've created a function called convert to categorical, and for every column in my list of columns, I'm going to find out how many unique values there are, and then I'm going to divide that by the number of records. And if the amount of if the ratio of that is less than 20%, I'm going to convert it to category. So if that's confusing, basically what I'm trying to look for are things like this yes, no, and convert those to categorical type, but something that's almost unique per each record, I don't want to convert. So I don't want to do a mapping of everyone's address. I don't want to do a mapping of everyone's name, but things like, a yes, no, or, is it a park? Is it a building? Is it commercial? Those type of things I want to convert to categorical. So if I run this real quick, it'll just create the function so that I can use it. I'm going to run this on my object type columns. And there's one key call out here is that I do have an object type column that's called geometry. And this is from that Geo Pandas that we brought this in. Geo Pandas is not Pandas, it's an extension of Pandas. And a lot of these methods don't necessarily know what to do with this geometry type. So I don't want it to crash out. So I'm just going to remove the geometry type from my list and then run this function across that. So as I run that across that, we can then check how much memory that's going to use. This will take a moment or so. But as you recall, that GeoPandas, it's an extension, and so not everything is going to be supported for all of the traditional pandas-like operations. Most of them are. The idea is that rather than working with a shapefile completely differently, you can work on it almost like a data frame, and most of the stuff is supported, but not everything. So what I've done here is I've just run a .info with just turning off all the column stats off. And I can just see, now we've got a much smaller data frame. It's more than half the memory consumption, which is great. We now only have 4 columns that are object type, which is also great. The rest of them have all been converted to this category type. So this is great. We can work with this a lot quicker. Let's see here. Next, we might want to kind of go in and do some profiling. So I'm going to run this and explain it while it runs. There's an additional library out there called Pandas Summary. And this is a library that's been created by just some people that really wanted some reusable library to run some very simple statistics on their data frames. If you are familiar with pandas, there is a .describe method, but it provides just very, very basic information. And this provides much more detail that I think is very, very important. So for example, if I want to dig into an individual column, it creates an entire data frame of these column statistics. And what I can see here is the mean, standard deviation, variance, min, max, kurtosis, skewness. I can see the top correlations, which are really important because as we're trying to do maybe like a regression model on this or run some kind of machine learning algorithm on this stuff, if we've got variables that are very correlated, like in this case, estimated market value of the land is going to be very correlated with the total value of the entire property. It's also going to be very correlated with the tax capacity. It's also going to be very correlated with the estimated market value of the building on there. So we might only want to use one of those columns in our analysis and exclude the other ones. So as you can see, this kind of gives us some great information here to kind of quickly dig into stuff. It shows us where most of our data is. This isn't a really great histogram, but it does spit out a histogram here that you can quickly see kind of what's going on there. But if you want to just look at the top level to see kind of, okay, across the entire data frame, how many values do I have available there? You can scroll through all of these and you can see things like, okay, acres deed is constant. It only has one value. Everything in there is exactly the same. Well, I probably don't want that column then. There's other fields in here that are almost all blank. We might want to exclude those from the analysis. Landmark, completely empty. So, some of these things that we can quickly get rid of and just shrink down the data set more. Because if we're not going to use it in the end, why would we lug it around with us throughout the entire analysis? So what I've created here is just a list of all the columns that I've identified ahead of time to drop out. And so I'm going to just drop those out of my data frame, run that. And so now I want to bring up this other library that I really like that's called MissyNo. This is, again, just another library that's available out there that, rather than looking at this data set and scrolling through to find out where data is missing, I really like this chart. Because if you have something that's like time series, you can quickly see, like, are there problems with the sampling method? Where maybe there was a holiday and no one gathered data during that time. You can quickly find out if you're joining or appending multiple data sets together. Did you do that wrong? So this quickly gives you some quick information at your fingertips, so you can see, okay, these X uses are almost always empty, so maybe we should just remove them. But they do have some information in there. So I've wrote another function here that deletes things that are almost null. So it takes in the data frame, the columns that I want to work on, and then I have set a threshold to basically say if there is less than 1% of the data in that column populated, just remove it. So that's what this does for each column in the list of columns we provided. Count out how many non-null rows we've got, and then find the ratio of that. If it's below our threshold, delete the column. So we'll run this real quick. And once again, we're just going to skip out on that geometry type because that's where all of the Polygon vector data is stored. But none of these functions really work on that, but that's fine. We don't want to remove that anyways. So we'll just leave that there. So we delete that. And now what does our data look like? Well, we started with 80 columns, and now we're down to 47. So that's good. And I think we have about the same amount of rows, which is to be expected because we've only been getting rid of columns. So now that our data set's ready, you guys might be like, okay, we were talking about geospatial information. When are we going to actually get into the geospatial information? Well, here we are. We're at the point where we're going to start talking about that. So this information, or this data set that we've got here, contains geodesic features. In this case, it is going to either be in the form of point, multi-point, line, multi-line, polygon, multi-polygon. And really, we only care about, for our tax parcels, if they're polygon or multi-polygon. So we're going to filter out anything that is not that. So we're going to remove everything else. And the key thing here is that point might be a place where you're currently located. Multi-point might be, here are all the observation points for collecting information on lake quality within a specific lake. A line might be a road, it might be a power line. Multi-line might be transit routes, it might be sewer systems, you name it, something that's just kind of two-dimensional, or yeah, one-dimensional. And then you've got polygon data, which is kind of these arbitrary shapes that are going to try to represent, lakes, properties. It might represent city boundaries, things like that. And then multi-polygons might be something like a condo where, there's multiple people that own it, but it's all part of a larger parcel that's kind of that whole unit. It might be a park. It might be land that has easements on it. It might be islands. You can imagine the United States. We've got the United States, and then we've got Hawaii, we've got Alaska. If you were to plot the United States, that would be a multi-polygon. So one thing to keep in mind as we're working through this data is that geospatial joins and searches are very computationally expensive. To try to work through this data, you should really think about breaking up into pieces and processing them iteratively. So you don't want to just try running every possible thing and calculating out every possible tax parcel in trying to figure out what the closest lake to that is. Otherwise, you will be sitting at your computer for days or weeks. Instead, if you break it into smaller pieces and window over it, you'll be much better off. And what I mean by window over it is that, as you can imagine, Minneapolis, like many cities, has boundaries that are set up by rivers or lakes or something like that. So if I care about how close a property is to a lake or a river, if I am artificially subsetting my data based on the Minneapolis boundary, I might not be including the actual closest lake or the actual closest river because I'm artificially subsetting my data. And so you may want to create some kind of buffer areas around that. And we'll get into that in a little bit. So we're going to filter this down just to Minneapolis data sets. And you can see that after we do this, instead of having 400,000, we have about a quarter of the data we started with. So this should help speed things along. And so throughout this whole time, you guys have just been talking about geospatial information and how there's these different things called polygons and shapes, but we haven't really seen any of this stuff. So let's bring in the lake data. So if we scroll back up, the first set of data that we brought in only had the tax parcel data. All of these areas that are white, these are water features. There's actually no information in there. You can kind of think of them as not being present. They're null. They're not in there. And now we're going to overlay a second set of data to bring those things back in. And then eventually we'll overlay a third set of information that will provide water quality statistics for those water features. So let's go back down. Apologies for the scrolling screen. That's probably going to blow right by on this video. So again, we've just brought in a water data frame. We're going to set the index and sort it. So we're going to just quickly look at what this data set looks like. We can see that it has much fewer columns, and it's got the geometry type here, so we can expect that. But also, interestingly enough, it has the area of the shape. So in specific units that are listed out in this metadata here, you can find out how big are the lakes. You can find out the length of it, which I think is the maximum point-to-point distance across the water feature. But if we plot this, we can see here are all of the water features across the Twin Cities area. We can see lakes, we can see streams, we can see all these different things. So truly, Minneapolis is the city of lakes, and Minnesota is the land of 10,000 lakes. So going into this, let's see how much missing data we've got. We've got a column here called alt name that is very sparsely populated. So one thing that is very important is if you have subject matter experts, highly recommend reaching out to them. Through our MinneMUDAC competition, we did have some contacts at Met Council that were able to provide additional information on this data set, and they let us know that all of these points here, these are seasonal wetlands. They can be runoff, drainage ditches, anything that collects water throughout the Twin Cities at any point of the year will have a water feature in it. So I don't know about you, but the local drainage pond for the highway doesn't have a name near me. So likewise, that's why this alt name does not have anything in there. Same thing with the name for DNR. The drainage ditches and things like that do not get water names. Only the major consistent water features are going to get an official name. So when I said before that geospatial calculations are very expensive, they are very much so. So if we want to figure out kind of how close certain tax parcels are to a certain lake, we don't want to look at every single lake on this data set. We just want to look at a specific lake. So I am going to pick my favorite lake around the Twin Cities, Cedar Lake. But as soon as I search on this stuff, I see, well, there are 2 lakes here. And I unfortunately don't know much about this OWF. It's open water feature. It somehow ties in with kind of a DNR hydraulic um, hydraulic unit uh, code that they have, or a HUC. But I'm not very familiar with kind of how to decode that. So I'm going to just go purely off of what I know. So I'm going to just plot these things, and this is using that geoplotlib, and I can see two shapes here. If you are not from the Twin Cities, you're going to go, okay, cool, there's two lakes. That's not very exciting. Um, well, I go bike around this lake very often, and so this is the lake that I want. So I am just going to filter out down to this lake. So I'm just going to set my data set to just be this one lake. But if you were going to do this at scale, highly recommend you use something more like a unique identifier like this open water feature ID to correctly identify the lakes that you're looking at, rather than relying on visual cues like this. So next, if we want to know what properties are next to Cedar Lakes, or next to Cedar Lake, you might also want to know some context about the lake that I love so much, is that it has a public trail that goes all the way around it. So there's not going to be any private property that actually touches the lake. So we need to expand our search beyond just what touches the lake. And we can accomplish this by what's called buffering. So basically what this is we take the lake and we just say expand the border of it by 100 meters. And so we can do that right here by just buffer 100. We can plot this out. We can see here's the lake, here's the buffer zone. And so I don't particularly care about the other attributes that are in this data set, so I'm just going to remove those so that we don't have to work about those or worry about those. But to be able to find the properties that are really close, we need to do a spatial join. And if you can imagine trying to figure out whether a property, a weird, funny shape, overlaps with this weird, funny shape, is probably pretty difficult. A much easier way to do this would be to create what's called a bounding box. And so what that is that I'll plot this out real quick after it runs. But basically what it is it creates the smallest rectangle around the shape, in this case the buffered Cedar Lake, to basically make searching or narrowing down our data set much easier. So now basically you have to just find, is one of my points greater than this index point, less than this index point, greater than my y intercept, and less than my y maximum value. So this makes it much easier. It's 4 conditions rather than having to check each individual area. And what this does is that by using that spatial index that we created up here that I kind of just glossed over, this is just basically creating kind of this this bounding areas of these points to know where certain things are. So after I do that, we can see that we now have filtered down the 100,000 different things very quickly down to 457 properties. But obviously, not everything within this blue box might be really close to the lake or might be the first property within the lake. So now we might want to do some more precise matches. And so now we're looking at potentially where specific properties overlap with this red blob, rather than are they just within the blue. So we're going to look for any properties that are included within this blue box, and then filter them down to anything that intersects with the red. So we can do that. Again, this is fairly quick now because we've got much less data. And so now we can plot this out. We've got 208 different properties around the area. So now you can see here are all the properties near here. You can see that there's a whole bunch of weird shapes around here. I know that this one right here is a park. This big white area is a wetlands. This gray, long, skinny area is a public bike trail. And I think this other area up here is another public park area. So pretty neat that you can see everything that's within 100 meters of the lake and narrow it down. So let's just make a data frame that is only these matches and just filter it down. We're also going to create a new column that's just called Cedar Lake so that we can join that back. So that's done. So now what we have is we have the tax parcel information paired up with the lake nearby, but we don't have any information on that lake. So what I've done is I've created a more simplified version of this data set specifically for this talk. That's just a data frame, it's just tabular data for Cedar Lake that is weekly observations of things like how much chloride is there in the water, what's the alkalinity of the water, the chlorophyll, how clear is the water, etc. And it's got a lake name for a key. It's got the coordinates of exactly where that information was collected from. And we can just do something very simple and join this information together on our other data set. It's just the same way that you join any other Pandas data frames because that's basically what we're doing. We've got our property tax data here. If I scroll over, you'll see that we've got our lake data now connected to this. And this is specifically related now to those 208 properties that are right next to the lake. So cool, let's look at this. Well, did I lie? Did I just say that we only had 208? Well, this is weekly data, so for each one of those 208 properties, you now have like 52 weeks of observations for that. I hope that that math works out, that it comes out to this number. There may be multiple observations per week. I can't exactly recall, but for this intents and purposes, let's just say that there's a week for each observation. And so now that we've got this information all joined together, one thing to kind of keep in mind is that some of this information is almost all null. So Minneapolis wasn't actually collecting information on basements for 2014. So that's almost all null. They weren't collecting information on the cooling systems of the housing, so that's almost all null. Heating, things like that. So what I can do is I can just say drop out any columns that are all null, and it'll shrink our data set down yet a little bit further. So 8 columns dropped out that were completely null. So now, based on this information, we've got all of our data sets joined together. We might want to actually find out how close are those properties to that monitoring station. And so we can do this by just simply saying, where is the center point of each one of those properties? So if I scroll back up, if you recall, some of these properties have some very weird shapes. But for the most part, the residential properties are all pretty regular. These are all going to be like the houses, and they all have kind of small, tiny lot sizes. And so the centroid of these are going to be right in the middle, whereas the centroid for these other areas, they're not going to have property values anyways because they're governmental properties, they're park, things like that. So I don't really care that I'm kind of hand waving away things here by just using the centroid. If you wanted to get more complicated, you could do a more edge-to-edge calculation, but again, that's going to take more time. So what I'm going to do here is just calculate out the centroid of those locations. So it creates a bunch of points. But if I look at these points, these don't look like GPS coordinates. And so you might wonder, like, well, what do I actually have? Well, GIS files are actually going to use things called datums, which are kind of setting the origin of the coordinate systems. And we need to convert these into something that is more human readable into kind of that latitude, longitude. There's an article that I've linked here that kind of goes over this concept in detail. And yes, if you're wondering, there is an entire Stack Overflow for GIS information. They've got their own problems there, and so they have their own message board and question and answer section. So definitely check that if you've got more questions. We can see what our starting projection is, which is kind of this datum, the set of origin points that we're going to use. We can see that it's a certain standard here. We can convert it to the normal lat and long by just running this CRS2 or this 2CRS to this different format. And we can now see that, hey, these look a lot more like latitude longitudes. The problem is that these are shapely geometry points. And for the next library that I want to use, it needs them to just be tuples. So what I can do is I can use a lambda function, which isn't really super easy to read, but you're going to see that used a lot in data science because it's kind of a quick way to do a quick one-liner. The way this one can be read is for each row, create a tuple out of the two columns or the two data points within this point system. So there is the latitude, longitude, and so we're going to create a tuple using both of those. So if I do that, you can now see, hey, I've got tuples that look like latitude, longitude. You'll notice that I flipped them so that it is, in fact, lat long now instead of long lat. But the key thing is that if we want to do distance calculation, you need to make sure that you're not using Euclidean distance, because if you recall, the further that you get towards either of the poles, the closer that your longitude lines are going to converge together. And so weird things can happen. So make sure that you use some distance calculations that take that into account. For the most part, it's the amount of spacing that we're talking about isn't going to matter too much, but definitely make sure you take that into consideration because things get real weird as you get closer to the poles. This can lead into a lot of distortion. So the common map projection that you saw in school is called Mercator, and you can see here's Greenland overlaid with Africa as if they were in the same spot using that projection. Really, Greenland is not nearly that big. Africa is huge. It's about like two-thirds the size of Asia, but because of the way that things get distorted when you flatten them out on a map, Africa ends up looking a lot smaller because things aren't as distorted, whereas things towards the poles get much more spread out. So definitely keep that in mind as you're looking at geospatial information, how that distortion can happen, and make sure that you don't fall prey to it. So as I mentioned, you don't want to use Euclidean distance, which would just be kind of like an XY grid and calculating the distance between the 2 points. The Earth is not flat. We need to use some formulas that keep in mind that the Earth is not flat. So there are two major ones that are out there that GeoPy uses. There's the Vicinity Formulae and the Great Circle Distance. The first is a little bit more accurate, given the fact that the Earth is not actually a sphere, but kind of a spheroid. I think it's a little bit more squished out in the middle, but I could be wrong on that. So if you're doing something that needed to be super, super precise, use the Vicinity formula. If you just want something quick and dirty, the Great Circle Distance calculation will get you there. It's also a little bit easier to understand. Basically what it does is it finds out if you created a circle that went all the way around the Earth, if the Earth was a perfect sphere, what is the arc length between your 2 points P and Q? One thing to keep in mind is that at the scales that we're dealing with is that the Earth is hardly arced, but better safe than sorry, and it does handle our latitude, longitude, data points that we've got. Sorry about that. Just needed a glass of water. So now if I want to actually calculate out the distance, I can create a formula here that is basically for each row in my data set, I'm going to take these two things in and calculate out the distance in kilometers. And I'm going to create a new piece of information called distance to the station, or distance to the place where we collected information on the water quality. We're going to just store that information in a new column called distance to station, and we're going to call this function on the data frame, applying it on each row and putting it all in there. But once we have that, we don't actually need the coordinates anymore for our future analysis, so we can just drop those out. So, oops, I already ran this, so of course it's already going to be there. So now we can see we've got all this information. We can see that the distance to the station is calculated here as a field. So now we can use that as an attribute. They are all the same on these because they're really close. If I made this a little bit bigger, we can see that they do in fact change. I didn't just kind of assign one value to everything. So we scroll down here, we start seeing that there are different numbers. And this is mostly in part, I think, due to kind of some rounding of where our data points are given. So last but not least, we've got this data set. Now you might want to run some regression models on it. You might want to do some future analysis on it, but you don't want to lose your work. So you might want to save this stuff out. So if you wanted to keep out the tax parcel information, we still do have the geospatial information for the tax parcel. It's right here in this geometry column. We can save this out as a shapefile by just merely saying data frame to file and then specify our file name. One thing to keep in mind, though, is that it doesn't really create a file per se, but it creates those like 5 or 6 different files that all work together as a shapefile. So that's where we're going to land for today. I've got a little bit more involved GitHub link out here that you can go to. Social data science, geospatial data with Python. It goes through a little bit more data manipulation with that last data set that was tabular, does some pivoting, some things like that. I just found that that was getting a little bit tedious to kind of talk through, so I cut that out, but you will see that in there. We're going to have this out on YouTube. Keep in mind, we're going to start doing some more talks here. And last but not least, at General Mills, we are hiring another senior data scientist. We're hiring a consumer insights data scientist, a big data platform engineer, and a senior master data management engineer. So if you're interested in those and would want to join my team and work on some cool stuff, definitely consider applying for a job at genmills.com/careers. With that, we'll leave it at that, and let me know if you got any questions in the comments. Thank you very much.